Hello, everyone. Welcome back. So this is a CC3 mesh processing, and we have four excellent and interesting papers from SPM. And the first paper is local DeWall, building scale 3D Delaunay triangulation on a single GPU. The presenter is Wuheng from the University of Science and Technology of China. Thank you.
Thanks for introduction. Good afternoon, everyone. I'm Wuheng Gao. Today, I will present our work, local DeWall, building scale 3D dynamic triangulation on a single GPU. This is a drawing work with my advice. Three-dimensional dynamic triangulation is a fundamental structure in geometry computing. It is widely used in visualization, finite element methods, volumetric meshing, and various simulation pipelines. As acquisition and simulation data continue to grow, we increasingly need to handle one size with hundreds of components or even millions of samples. This makes a high level of GPU than direct kernel element and important. For large one size, a practical GPU parallel strategy for constructing the direct triangulation is to decompose the problem into many local computations. Instead of reasoning about the whole triangulation locally, we let each one process its own neighborhood in parallel. This gives us a single and scalable view of the computation. Local triangulation structures are built independently, and then combine it into the global dynamic triangulation. A natural local structure for this one-wise strategy is the Delaunay Weiyin. For each point, we can construct this Delaunay Weiyin by taking the union of all Weiyins. We recover the full Delaunay triangulation. Equivalently, this process can be done in the DeWall space, that is the DeWall monoid of same point. For 3D standard triangulation of the GPU, Xiao-Diao proposed an early method based on batch inversion and parallel bilateral free flipping. However, their method first built a near standard triangulation on the GPU and then transfers it back to the CPU. Final prepare using adaptive star speed. Therefore, it is not a fully GPU parallel implementation. Another related method is specialist monoid by Weiyin, which constructs monoid cells through half-space intersection with nearby points. To reduce the complexity of the naive monoid cell intersection method, they introduce the radius of security, which defines a region where points are chosen for half-space intersection with the parent monoid cell. However, when the radius of security cannot be reached, which could happen for some in their method, the resulting monoid diagram is likely to be incomplete and cannot reliably produce the Weiyin binary mesh. A more relevant comparison is our own work from last SPM, PDT. PDT is also based on half-space intersection, but it improves locality using the local Delaunay lemma. It directly outputs a direct rectangular mesh, and the construction is fully GPU parallel. Overall, PDT achieves about 3 times speed up over the speed of light. In the half-space intersection method, all the tetrahedral in the Weiyin share the same central vertex. Therefore, it is sufficient to store only the boundary of each local Weiyin. We record first the indices of the different points, then the local triangle connectivity among them. Well, this works for half-space intersection. It is quite memory heavy. For this rather small neighborhood, it takes a total memory footprint of 78 bits. As runtime performance on the GPU is limited by memory bandwidth, reducing the size of this local structure is a key point for optimization. So the question is, are we avoid slowing the full triangulation? Let's begin with the full dynamic Weiyin of a target point A. Note that when we look at the set of Weiyins for all the points in the point set, each tetrahedron will appear 4 times. In other words, each tetrahedron will appear in the Weiyins of all 4 of its vertices. As such, we can discard a tetrahedron where point A is the leftmost or rightmost vertex in X order. All the remaining tetrahedral cross the plan X equals XA. We call this subset the local DeWall of A, and the plan the local DeWall plan. For each dynamic tetrahedron, we solve its 4 vertices by X coordinate. Then this tetrahedron will be found in the local DeWall of the middle vertices. So every tetrahedron in the global mesh will appear in some local. And the union of all local DeWalls, the complete triangulation. We found that the local DeWall can be represented much more compactly than a full binary mesh. Instead of explicitly storing the triangulation, we can instead store an ordered list of points. And that is sufficient to infer the triangulation at runtime. We will use the set bit of the indices to distinguish points on either side of the local plan. From this ordered set list, the whole triangles can be reconstructed implicitly. Take the first triangle as an example. We use two consecutive points in the list and find the nearest previous point with the opposite stand. In this way, each triangle can be recovered from the list without explicitly storing the triangulation. The next question is how to build the local DeWall efficiently. A standard composite intersection algorithm keeps the closed convex volume myself by the bisector plan. However, in our case, the local DeWall is only a stripped subset of the one ring, and its store becomes a polygon in R3. This makes it difficult to adapt composite intersection for our local DeWall. We propose to construct the local DeWall with a transform method. The idea is to start from an initial direct tetrahedron on the wall. We choose the direct tetrahedron intersected by a target ring on the plane as the initial tetrahedron. And then walk to its adjacent tetrahedron along the local DeWall plane. On the traversal from space where it started, the loop is closed, and the local DeWall for this vertex has been completed. We can see that our local DeWall allows significantly reduce memory traffic. By replacing explicit triangulation based on volume storage with compact local DeWalls, our method provides repeated reads and updates of mesh conductivity. Furthermore, the traversal algorithm is local and read-only, leading to much reduced global memory access and better GPU cache behavior. Together, these two designs reduce global memory traffic by about 10 times. Our implementation follows the similar organization techniques as done in PDT. We use the bucket data structure to support sphere search in order to find nearby candidate pods. Since the complexity of the local DeWall construction varies from point to point, especially in those scanning tests where the point distribution is sparse. For example, near the boundary of the convex ball, the runtime complexity of our traversal algorithm can increase significantly. Therefore, also adopt a two-stage kernel design to improve workload balance across GPU suites. Now let's check the results. We first evaluate our method on three nearly distributions: white noise, turbulent gray, and blue noise. Compared to PDT, we can see our method consistently demonstrates higher efficiency according these distributions. While our method is being designed for the default distribution, we also test non-uniform distributions generated with different density functions. The number in bracket are acceleration compared to PDT. We can see that our method remains stable under these non-uniform settings. For the more challenging Laplace distribution, our method is more than 4 times faster than PDT. Here we benchmark our method against state-of-the-art CPU and GPU baselines on uniformly distributed one sets. Across the tested input sets, our method achieves the lowest runtime. For 10 million points, it finishes in about 0.4 seconds, which is more than 2 times faster than the state-of-the-art and much faster than parallel CPU implementations. Here we report the normalized runtime measured as the average time of million points. For extremely large inputs, the output triangulation may not fit entirely GPU memory, so we switch to batch mode and process about 1 million points at a time. The vocal lines on the right indicate this switch to batch processing. Our experiments show that to produce 3 million tests, our method takes only 20 seconds, while Gmash requires 53 seconds for the same task on their 64-thread CPU. We demonstrate our method on restricted dynamic triangulation. Our method does not yet support constraints of any form, including boundary edges or weighted. Hence, we currently cannot recover a triangle mesh as the boundary of the output dynamic triangle mesh. As a remedy, in this application, we sample points inside and around a boundary surface, then compute the unconstrained 3D dynamic triangulation. Finally, we remove tetrahedron that lie completely outside the surface. Our method can be used for efficient mesh optimization, such as Floyd's iteration. Here, to generate CVT, the sample points move iteratively during optimization, and the underlying dynamic triangulation has to be updated many times. Our method makes its repeated triangulation steps highly efficient on the GPU, along with the point optimization step. So why do we call our method local DeWall? As many of us know that the name DeWall, which has existed in the literature for quite many years. Indeed, our local DeWall is related to DeWall, but only in two sense. First and foremost, our method is now based on the original divide and conquer DeWall algorithm. We picked this name because of simple geometric resemblance. Both involve simplicities intersecting a plane structure. In our case, the structure is local to each port and built independently on the GPU. To conclude, we propose the local DeWall, which provides a compact encoding of the 3D dynamic triangulation as an ordered matrix of one. We developed an experimental method to construct each local DeWall by traversing adjacent tetrahedron, drastically reducing memory footprint and traffic. As a result, our method achieves more than 2 times speed up for state-of-the-art and scales with billion more dynamic triangulation on a single convertible GPU. For future work, we plan to optimize the algorithm for non-uniform distributions and extend it to support constraint triangulation. Thanks for listening.
Okay. Well, that's presentation work. So let's talk with the question. Any question? Yeah.
So, just a quick question. I know that lots of people need the volume diagram instead. So Xian depends on for plus plus, etc. Because you can actually the Delaunay. Have you thought about transforming what you found on the GPU into a volume diagram, meaning to dualize your construction so that you can output a volume mesh instead? And would that be faster than something like volume plus plus that's limited to CPU?
Do you mean that translate the dynamic migration to polynomial measure?
Exactly.
That it's straightforward. I think it's I don't know how to say, but it's easy to transform the dynamic calculation to polynomial measure. Since the polynomial one is the mass there center of the generator.
Yeah, but you need to compute this if you have a billion point. It's not trivial matter. So my question is, if you do your local DeWall thing, and then you transform into a volume mesh, is it faster than doing directly vol plus plus type of algorithm?
Yeah. the computer the word meshes for learning is the straightforward form of mesh. We compare it.
Thanks.
Any other questions, audience? I have a question. So when we use these two filters, one of the surface constraint, the second is non-uniform. But I see some result non-uniform distribution for the input function. So yes, what do you mean here? Non-uniform? But it looks like you can working on some density-wise changing of the function.
Non-uniform it's still I think it's still for some non-uniform we can wait as well, but for some for non-uniform it's really we can also compare for the decision method.
So what's the challenge for the non-uniform? Do you have any thoughts here?
Maybe for example, graphics it's very heavy to use the exact graphics on the GPU.
Okay, thank you. Any other questions from the audience? If not, please set speaker again. The second paper is Weiyin supervised learning for 3D mesh segmentation while the pixel level labeling. And the presenter is Weiyin from the City University of Hong Kong.
Thank you, Chairman. And also thanks so much for all the organizers of the conference. So let me know. I think this time is a joint work with Belgium and also in collaboration with that PLL and so Chen. Actually, this work is mainly about 3D mesh segmentation. So it's mainly focused in that area. However, we apply deep learning techniques to achieve the final segmentation. I think normally the work should be presented by Dr. Wu, but who cannot be here today, so I will present everything here for today. I think for the following, I will briefly highlight what we have the main procedures, how to achieve the final segmentation results, and then briefly mentioning about the conclusions and also future work. So basically, the main motivation actually is the following. If we do 3D segmentation using deep learning techniques, usually in order to do the training, we need to label the input dimensions extensively with all the with many steps. In order to do that, actually it's very time consuming and tedious. So the main idea is that we develop a technique where we apply a simple sketch-wise labeling on a 2D image for the 3D mesh. and then we through a further training learning process, and finally we could achieve 3D mesh segmentation. So the final results actually could be used in two directions. So first of all, the final results we push here can be applied as for labeling of meshes of for different learning applications. Secondly, actually, the results can also directly used for as segmentation results. So basically, it can be used for upper learning process. It can also be directly used for segmentation. So here is the main ideas what we're talking about. Basically, give an input mesh. So basically, it's triangle mesh. We produce some views from the 3D mesh. And then we do a simple labeling going through a simple sketch somewhere here and there with the most important areas. And after that, so using such a simple the sparse labeling, and then finally goes to a further actual tool learning process, we can achieve the final segmentation results. This is hopefully it can be used as segmentation results, and also we could be used as 3D labeling for other applications. So that's the main motivation for what we're doing. So usually from the initial labeling, actually usually we produce about 2 to 5%. Actually depends on how many units we use. So where 2 to 5% the triangles has been labeled correctly as what we want. So this percentage depends on how many units that we use. So in that case, the main motivation is that we use a simple 2D labeling to achieve complex 3D segmentation. I think that's what we pretty much are doing. So useful simple 2D labeling and then going through the further transformation and finally we will achieve the segmentation of an input mesh of a single input mesh. Here you see an overview of the whole procedure. Basically, it's performed in three different phases or steps. The first step is made about the 2D labeling. So basically, from some selected views, and then we sketch the main areas we want. And after that, in the second phase, we call instance specific label propagation. The main reason is that after initial labeling, actually the area of the final meshes that has been confirmed may not be that much, like we mentioned, 2 to 5% or sometimes 10%, may not be that much. So we perform some kind of it's like region moving. So it's for mesh, further propagation such that we can achieve the segmentation. After the second phase, although the results look already normalized, however, if you look carefully about the partition boundaries, may still be not that smooth. And then we further apply another further learning process and where we can use the boundary, making the further smoother. So that's the main steps we follow these 3 steps or phases. I think the main contribution is mainly first of all, the main idea basically, if you do 3D labeling, it's very complicated, very difficult. However, here, if you go through 2D labeling, it's very easy. Secondly, for the interactive specific propagation, mesh propagation, actually we apply the existing procedure. We apply that learning approach for here so that we could achieve what we want for the segmentation. And finally, for smooth actually is also we apply another procedure. It's also learning approach and then you can further improve the force boundary so that it can be smoother and smoother. So that's the main work in preventing work. So for phase one, step one, we're talking about 2D labeling. I think what we have done is so based on input mesh, the architects of input mesh. First of all, we start our main architecture, and then from that architecture, we find out and best view from I think about 50 directions. Based on that main view, and then we can further produce easier 3 view or 6 view for the 2D labeling. So which means that for 2D labeling, can use easier single view or 3 view or more than 3 views. Most of them use 1, 3, or 6 views. After that, of course, from the 2D image labeling, signal labeling, we need to further map the 3D meshes. That's a simple procedure. So it's a mapping process. So that's the main work in phase one. Here you see some of the examples, 2 examples from 2 data sets from the literature. And the first one is here. You see for this case, we picked up 6 views, and we you see for each view, what sketch we put there for the later segmentation. The second example is a Wuheng body model. You also see 6 views we picked up. Actually, these are optimized actually, it's from the main view, and then you can further produce 6 views that's standard views. So from the first view, it's the optimized view. So in any case, these 2 examples, we see how do we produce 6 views and where do we mark the sketch for labeling. So the main observation here is that after we map the stable sketch to 3D meshes, of course, we can only confirm balanced monoid triangles for segmentation. That's really, of course, is not enough. So what we need to do to achieve finally for the complete input mesh, we want to partition into really regions, meaningful regions. For that reason, and that we go for the second phase, and that we call instance specificity, so vector learning approach. For this case, actually, it works a single mesh by single mesh. The main idea is that from input mesh, and that based on the 2D labeling, we apply an iterative process. So from this only a few percent of the triangles going through the learning process, it will go finally you can achieve the total partition of the whole input mesh. So it's an iterative process. For each of the process, it's a deep learning approach. So that for phase two, however, in this case, is a specific, which means that actually for the learning process of training, we only apply the results what we have for a single example, for a single object. We do not apply many other model training. And we also use actually it's a very simple graph. Contraction is a very simple graph. Basically, this graph collects the main information we need, for example, what the neighborhood information we need, like curvature information is a far distance faces with each information, and that goes through the training process. Then you can find the activity function. Actually, for this training process, we use in total 140 parameters of variables for the training process. These are the parameters that for like verification, the prediction information. I think it's the phase wise. So computation produced in regular computation essentially and also stop hardware producer like Chen nearby and also publishing. Altogether, there are 114 parameters we use during the programs. The main training and loss function will optimize the path size manually. First was starts oriented. So from a few confirmation, gradually we achieve more and more resolution. Triangles segmentation. Second, of course, we infer confidence labels. Usually, if we, of course, we gather the ranking of the confidence of the manager, the higher the manager. Finally, reinforce the geometry of where smoothness later one energy. Here you see two examples for the illustration of swap. For this case, let's compare the amount of techniques SVP from the here is now methods second definition is current training. For this case, actually we also differentiate using the first data sets, error one. It means like in this case, we only use the single view for the whole labeling. And whereas this case is the first the three views design six views. And also another example, student age. What you see is that after the second phase, you see we could already achieve and a higher percentage of phases which are partitioned already well compared to the school partition. Actually, the initial data is getting there, but we know the answers from initial data. So that's after the second phase. However, the problem here is that after the second phase, actually, if you look carefully between the regions, partition the regions, the boundary may not be smooth movements. So what we're doing actually, we apply a further training process. We are actually in this phase, we produce multiple models. And after this phase, and also after basically it depends on the confidence level after this we further of course have from the battery, of course we use the most reliable phases and finally we show statement type and work paths for final environments in long-term curriculum results. I think this is one of the final slides. So here we come weak supervised learning. So basically it means that we only use minimum information very good efficient and collect for the final whole training process. Here you see three examples. You see with this also our maximum with the uses structure class from the larger smoothly absorbed. See the however, you say that the main purpose for maximum is not to mean that we can achieve always better than others. It's not like that. It's merely to achieve something which is very simple, to issue the 2D labeling. Otherwise, it's very difficult to achieve. So final conclusion. So in the other case, we propose an efficient for efficient 3D mesh segmentation. However, we issue very simple 2D labeling or 2D mounting. Basically, if you compare if you typically it's operation, otherwise it's very tedious, but here is very convenient to use. And it's also very low cost of platform labeling. Maybe just mention future work. Actually, first of all, for the second phase, actually we're talking about the instance circuit training, where actually each time we are only do for a single model. You may imagine if we produce that also many others. That may also be the understanding. And secondly, for free progress about the battery. Of course, we improve the battery already afterwards, make it as smooth as possible, but still, of course, there's a lot of space. I think that's all. Thank you. Yes,
Thank you for the speaker for the nice work. So, any questions from the audience?
Thank you for the last presentation. Maybe I missed, so I just wanted to ask in which phase of your pipeline the different views are put together?
Only is the first phase. So during the first phase, we can use single view or three view or multiple views user and six. Actually, the main purpose for that phase is for 2D labeling. After that, we map the form pixel map back to triangles.
Okay.
So right for the initial phase where we use views. Otherwise, only the
yeah, sure. And is it the human annotator who selects the views, the different views, or you choose automatically?
Actually, I should say automatically. It's manipulation reading of the original model manipulation. From that interpretation, we do an initial optimization. I think from the orientation, we pick up the axis, we find the optimal view among, I think, about 50 samples. The main purpose is mainly for collecting view where we can cover most areas of the model. Based on that view, the all other serial systems are needed.
See, the very last question. Do you, in the you showed the method is really good in locating real 3D segments, so volumetric features. Do you think you can train your method to locate also 2D patches that are unique, for instance?
I think that is impossible. Actually, in my course, we before earlier as worked on the image processing. And that is the work that because we mainly work on 3D technology, so we apply what we need before for 3D image segmentation. Actually, there's some complications on as well. The first course about movie, for example, like medical image segmentation. Yes.
Thank you very much.
Any other questions? I have a question. So we're network, and like what you see here, the major contribution for this work is you can labeling on 2D, then you can 3D mesh. So I'm wondering, did you compare with some other existing 3D labelings? Like, do you have some numerical tables? I see some really nice.
Yeah. I'm thinking understand what you are asking. Actually, the main idea that's going through 2D labeling is very easy and simple. Although we did not produce any comparison in that sense. However, in general, if people are talking about deep learning techniques for 3D mesh processing, the labeling is very complicated. Say that's what's going to
Another question, do you think, because first I saw the title, I imagine you are labeling on some image for the natural image. Do you think you can working on these natural image pictures, which can, for that picture, 3D mesh?
I'm not sure that may be another area for model reconstruction from 2D image to 3D. For this work, the input is a 3D mesh. So we want to partition the mesh, 3D mesh, into regions to interest. So it's called 3D mesh segmentation. It's usually it's very useful for versus the area for category for segmentation. So the input is a 3D mesh for this case. The output is a segmented 3D mesh model.
Thank you. Any other questions?
I just want to learn the repeatability of your method. Let's say one person draw lines to image, so from 6 different views, and he again repeat. So he draw lines again. So the lines will be a little different tilted, let's say.
Yes.
What about the segmentation results?
Yes.
Is it different too?
Yeah, I would usually for the deep learning techniques we apply. There would be some uncertainties usually. The results would be fuzzy. Sometimes may not be exactly like. Maybe it's a confidence level. I think for the analysis for this case, it's based on our movement. It's based on 2D labeling, 2D marking from 2D images of our 3D model. So the results will be depends on where to be marked and how many times to be marked. You're right, exactly.
You might say. So the segmentation results will be hidden different. I don't know how.
Actually, you're right. That's marking labeling is very important. Usually, we have to mark sometimes. People like mistake about that area and should be following a region for each. So you're mistake about that way and that way marker behind somewhere in the middle. Or if some of features like that, just mark in the middle. But the other thing is, the labeling process compared to 3D labeling is very easy. Only compared in that case.
Any other question? If no, let's thank the speaker team. Thank you. Yeah, I just want to check the third paper. Also, okay. So, and the third paper is accelerating Hausdorff distance computation between triangle meshes while spatial locality. And the speaker is the Wenbo from the Wuheng University.
Hello everyone, my name is Wenbo. I'm from Weiyin University. We will talk more on accelerating distance computation on geometric patterns. I will explain the problem of the method for certain elements of experimental results. Let's start with the background. How do distance values was the case geometric value between two shapes? In this figure, the outcome is a source mesh, and the lower surface is a target mesh. For each point on the source mesh, we found the shortest distance to the target mesh. Most of these local distances are not found also. The hollow distance is the largest local distance. In the figure, this is shown by the mentioned value. This metric is important in mesh simplification, remission, and reconstruction. We need the largest possible error, not only the average error. The problem is cost. If both meshes have many triggers, exact computation in many nearest point queries. This is slow for large models and high precision settings. The baseline method uses branch and boundary with cascading all paths. If a model is strong, it can draw many triangles and multi-many subdivisions. There is still a key overhead in the subdivided stage. When a triangle is subdivided, new channel voices are created. for each child vertex. For each child vertex, the baseline starts on unit 0 point query from the root of the target WH. This is called start query, and it doesn't use information from the parent vertex. Each child vertex goes back to the previous root and performs the globe transfer. The key observation is simple. A child vertex is usually close to its parent vertex, so the unit surface of the child is often related to the unit surface of the parent. If we ignore this relation, many globular child cells become rigid. This is a cause where we want to reduce. The core idea is to use spatial locality during subdivisions. First, subdivision creates a child vertex near a parent vertex. Second, the child inherits the parent's unit surface and initial gas. Third, research a vibrating hole around its face. This gives a long distance value. Then we compare the long distance with the current global bound. If the local distance is small enough, the child vertex can be the Hausdorff maximizer. Then we plot it and skip the global image query. If the local result is not enough, we fall back to the global image search. The method is not replacing exact search with an unsafe approximation. This slide shows where the acceleration is using the full branch around algorithm. At the beginning, we build the AAB tree for the patching mesh. We also build the face-time Renjie matrix. This shows us which faces are Renjie labels. During subdivision, we process the new overseas. For each new vertex, we get the unit surface information from its parent vertex. This is the hierarchical spatial interpretation. Then we run the one-click neighborhood search, which is related face and adjacent faces. This gives a local minimal distance called local. Next, double counting decides what to do. If the local is below the global bound, which gives the BVH query. Otherwise, we run the global BVH query and use the local and global bound. The story rule stays the same as the baseline. We update the bounds until the required tolerance is reached. Now I will explain why this method is safe. The local value search gives a decent value. This value may not always be the only services, but it is still a well-known bound because it is a distance to a fixed bound function mesh. The planning rule uses this bound carefully. If the local is smaller than the current global bound, this point can be the maximum point of the hollow distance. So we can simply skip the global image query. If the local is not enough for planning, we fall back to the global image search. The global query gives the exact unit cell distance. This fallback keeps the same accuracy target as the baseline. With the speed up comes from skipping unnecessary image queries. It doesn't come from changing the final error bound. Now let's look at the experiments. The first experiment is general benchmark. We use 29 or 998 mesh pairs from the schematic dataset. The 20 meshes are simplified waves of the sub meshes. The pie chart shows the period of the hierarchical spatial installation. Having means that the unit surface of the child vertex is found by the inherited face or its local neighborhood. The result is strong. In 79.5% of the cases, the failure is at least 99.5%. This shows the mean during subdivision, parent and child vertices have strong spatial locality. So local search can handle most unit point queries. On average, our method is 2.14 times faster than the baseline. The median time is reduced by 69.4%. The mean number of BVH accesses is reduced by 97.3%. These numbers show that the method reduces the mean query cost. Fewer BVH accesses also lead to real-time reduction. The plots show an important trend. Large and more expensive cases benefit more. With deep subdivision, rapid queries grows quickly. In that case, spatial locality becomes more useful. So the method is very multiple complex matches and strict accuracy requirements. Speed is used only when the result is still correct. This slide compares the low and top boundary from our method with the baseline. The points are very close to the population remote line. This means the two methods give almost the same bound values. The maximum difference is very small. So the acceleration don't change the final result. This is consistent with the algorithm design. When the local bound is enough, we will safely. When it is not enough, we will the global image query. The final low and upper bounds stay consistent with the cascading upper bounds baseline. So the method is simple. We get the speed up by reducing repetitive queries by making the accuracy requirement. We also test hardware city high density overlapping match pairs. In this experiment, we use 400 dimensional match pairs. They have overlapping geometry, but their topology can be different. This is more challenging than a simple simplified match comparison. As a result, can be better. The average speed up increases to 2.55 times. Image access dropped by 170.6 times. Also, 78.9 model repeats time of image and list 99.5%. This helps us that deeper subdivision can make spatial locality stronger. Child states become close to their parents. The inherited DNA surface becomes a better initial guess. So this result confirms the V trend. The method becomes more useful when the baseline computation becomes more expensive. We also test several stress cases and limitations. For the large model, the method gives 12.29 times speed up. This shows that the method can be very effective when the query cost is high. For the some feature case, the method still keeps incentives and gives faster computation. However, the method is not always faster. There are two main limitations. First, for very simple matches, the subdivision is shallow. Also, the latency overhead may be larger than the benefit. Second, the method depends on topology. If the match can missing topology, the match for the structure or transform data, the value neighborhood may not be reliable. So the method fall back to the global image query problem. So our method is a space-for time trade-off. It works best for complex matches, deep subdivision, and strict accuracy settings. Let me summarize the main points. Hausdorff instance computation is manipulation point queries. In the baseline, many child overseas start global image queries. Our method use spatial locality to reduce these repeated queries. The method has three key parts. First, hierarchical spatial initialization. We use the patterns in the surface. Second, memory whole search gives a local outbound. Third, double brownie gives global image search with the local result and enough and simulate needed. Across more than 1,380 test cases, the average speed up is about 2.27 times. The heaviest is about 99.5% more than 70% of the data. The accuracy is still consistent with the baseline. For future work, we want an adaptive map as for suitable matches. We also want an adaptive search range based on local service culture. That's all. Thank you for listening.
Thank you for the investment. Any questions from the audience? Renjie, I call you, okay? Because I understand you recently published a paper and talk about GPU-based Hausdorff this. You have some great questions. Expect.
Right. Thanks. Yeah. So I understand all of this. We are all seeing images. Also, I mean,
Okay, another question. So, according to spatial units, or hash ratio, hash hitting ratio wasn't that high, or was it 30% of data? But how does that translate to spatial ratio actually time or well, twice?
Sorry, I mean, for your central question, can we discuss in the after session?
My second question, is it possible to quality management with GPU?
No, I don't have exactly.
But it's possible.
I have read to some papers about use the GPU to accelerate the Hausdorff distance function. In the future, it may the GPU may be using in this set.
Yeah, I think the increase solution basically we use some forms in parents and shows child. So I think it's exploitation. Or it's possible to combine with things to works this. Thank you.
So just a follow-up, looks like your mixer is like a jet, like speed up. So it can be combined on the CPU or the GPU. Am I correct?
This program is only usually CPU. Yeah.
And what's the baseline? You talk about it's 2.27 speed up. So what's the baseline method or implementation you are doing with? I mean, what's the baseline compared method for this speed up? Because you can go and write implementation altogether. This one is based on which method of implementation for this speed up? We can discuss on that. Thank you. Any other questions? Okay, if not, this next speaker